thank you. I'll give you a little bit of the experience I had prior to consulting. I worked first for the DuPont company and started in polymer science and then went into pharmaceuticals research with them. And I did transdermal drug delivery, oral sustained release, and a lot of systems that were developed by Alza Corporation, if you knew who they were back when. They were the first people to develop transdermal patches in the past. After that, I went to Johnson & Johnson and worked for Ethicon, and Ethicon's specialty is resorbable sutures. So I led the group that made the polymers that go into the sutures as well as the products that they create, like Vicryl and other resorbable sutures that are used today. After that, I went to Kimberly-Clark and worked on topical solutions for skin health using regular personal care products like diapers, incontinent products, tampons, and other things of that nature. And then I went actually back to the DuPont company because they started a joint venture with a company in the Netherlands called DSM. They developed a partnership called Actimax. The objective of that partnership was to develop a sprayable hydrogel that would be put into a surgical site before closure to prevent adhesions from occurring in surgery. That product is currently in clinical trials, and we'll see where that goes. Since the end of last December, I've been a consultant. I'm currently consulting for 4 companies, and I'm working on various pharmaceutical and medical device products. So today what I'm going to do is go over a few things that I've done some work in and give you a flavor of the types of materials used in soft tissue engineering. A lot of people may have heard of these injectable fillers used in cosmetic surgery. Well, those are one of the places these things go into. But they're also used in advanced repair in terms of wounds and doing things of augmenting the effects of soft tissue and to improve the soft tissue that people have. The other areas where it's used is reconstructive surgery. So let me get into this now. There's different classifications. There's natural or synthetic polymers. They have multiple characteristics. That's dependent on the preparation method, the type of charge, the structure, cross-linking, and function. So, as I said, the source could be natural or synthetic. You can make homopolymers, copolymers, or multipolymers. The preparations are usually simultaneous polymerization or cross-linking of a polymer. They can be non-ionic, anions, cations, zwitterions. Their physical structure can be amorphous, semicrystalline, or hydrogen-bonded materials. The cross-linking can usually be done by covalent bonding or intermolecular forces. Their functions are to be biodegradable, either stimuli responses or be superabsorbents. So in biomedical and pharmaceutical applications, most in terms of preparing these things, they're a result of a polymerization of building blocks to make polymers followed by cross-linking. Water is present in many of these polymers, and during the initial formation of the cross-link structure. The typical methods used in cross-linking are irradiation, chemical reactions, or physical association. Here are some examples of things that are cross-linked. And these sols represent materials that are compatible with the building blocks that you're trying to cross-link. And in every case, you're making gels of different types. So they could either be photocross-linked, thermosensitive, stereocomplexed, pH-sensitive, or peptide-based. Now, properties of these hydrogels, usually they're a continuous solid supporting a discontinuous liquid. A solid is usually cross-linked. The liquid is anything compatible with the network. Could be water, could be something else. Doesn't always have to be water. In terms of water content, these things can vary anywhere from 20 to 98%. And as you can see, you could start off with a small material, swells to a very large material. The characteristics of these things is the free water allows diffusion of solutes. Mechanical deformation is dampened by the viscous nature of the gel. The density of these things is usually matched to water. There's very low solids content, and these things tend to be lubricious. In terms of their structure, they could be static or dynamic, making them things like thixotropic. There's a lot of cases where you could take these materials, inject them through syringes, and once they put themselves in the area where they injected, they're solid again. So they contain and confine water in a three-dimensional shape. They provide elastic recovery and provide support for active ingredients. Most functional hydrogels are molecular. Although their pores can be relatively large, their strut thickness is usually in angstroms. And it's challenging to determine their microstructure. And these are two examples. One's a confocal micrograph of one, and here's an environmental SEM of another. So the swelling properties are influenced by changes in the environment, pH, temperature, ionic strength, etc. They can be biodegradable, bioerodible, and bioabsorbable. They could be permanent versus temporary, incorporate ester linkages, and can degrade by hydrolysis. So how the structure influences properties, it's either by pore size, cross-link density, water content, or your polymer choice. Here's some representative structures of materials that can actually make good hydrogels. So this is hyaluronic acid. This is very dominant in your skin. Your skin has about 50% hyaluronic acid in it. Sodium alginate is usually used in wound care. There's agarose. These are usually used for growing bacteria. There's starch that's used for hydrogels, as well as chitosan, which is usually derived from shrimp shells. And it's a deacetylated version of chitin, if you know what chitin is. It's usually the exoskeletons of shrimp and as well as insects. The structure and repeating units of common synthetic hydrogels are polyvinyl pyrrolidone, polyvinyl alcohol, polyanisopropyl acrylamide. There's itaconic acid, hydroxyethyl methacrylate, polyethylene glycol, polylactic acid. They're ubiquitous in the body. You often find them in mucus and tear films, cartilage, vitreous humor, and the cornea and tendons, and their microstructure provides critical functions. They're usually carriers or protectors. They're here for drug release. They can either be smart gels, tissue guides, used in vision, used for tissue bulking, or cartilage replacement. In other clinical applications, they're used for the treatment of urinary incontinence, stroke mitigation. Hydrogels have been injected into the heart wall to stiffen the structure and preserve the geometry of the heart. They are often used for soft tissue replacement and augmentation. In other clinical applications, there's load-bearing requirements, especially for things like cartilage replacement. In here, the challenge is creation of a conformable lubricious surface. Native cartilage cushions lubricates and spreads the load. It has naturally low friction and conforms to loads. There's a roadblock to minimally invasive procedures. Current procedures require tissue excision. So what you have to do here is create a biomechanically compatible synthetic cartilage. And current devices change the way the joint operates due to removal of meniscus and ligaments. So hydrogels may be suitable as cartilage substitutes, but their properties need to be dialed in correctly so that the mimic to original cartilage remains. So here's an example of a cartilage replacement technology some companies have worked on. This is by Johns Hopkins. It was a chondroitin sulfate system, and then another group developed double network hydrogels. Others include PEG scaffolds, which are polyethylene glycol or polyvinyl alcohol implants. In other medical applications, there's been work on a nucleus pulpus to replace that in the spine, do drug release. do tissue replacement for hard and soft tissues. So how do you adjust the properties of hydrogels? A lot of it is done by cross-linking and the extent of cross-linking. That determines swelling behavior, the mechanical properties, and uniformity. Also, water content influences mechanical properties. Here's an example of what cross-linking does in terms of the properties of the materials. And your polymer choice makes a big difference on degradation behavior, biocompatibility, and swelling activation. So here's an example of a gradient hydrogel where there's low water content here and high water content on the bottom. So the current uses of hydrogels in medical applications are as carriers or protectors. Like I said before, for drug release, there are smart hydrogels, tissue guides for nerve regeneration, in vision for contact and intraocular lenses, for tissue bulking, and also cartilage replacement, like I mentioned before. Now, that thing I mentioned about urinary incontinence, there's a profound quality of life impact here. So what happens is they're trying to develop a bulking agent that prevents this from being a problem. And these are not currently marketed, but they're in clinical trials, so this is something that could be of help to people who suffer from this situation. In stroke mitigation, it's due to myocardial infarction when part of the heart dies. In this situation, they'd like to inject a soft solid into the heart wall to stiffen it and preserve the geometry. For other applications, like I mentioned before, the idea of replacing your meniscus is conceptually simple but difficult in terms of matching load-bearing and cartilage mimics. So the other requirements for optimizing your performance include coming up with native cartilage cushions that lubricate and spread loads. The other is to have something that can be delivered in a minimally invasive surgical procedure, have something biomechanically compatible, and where cartilage replacement is mostly hydrogels. Compressive strength is important when you're dealing with loads. So here's an example of what type of recovery you have depending on the strain you have in your system. This is a typical response of polyvinyl alcohol under compressive load-unload conditions. There's another example of viscoelastic behavior of materials, and these images show you some of the things that can happen in terms of conformity of these hydrogels. So tear strength is another thing that's important. Once you create these things, you do not want them to tear easily, so coming up with the right composition to do that gives you a chance to determine whether you improve your tear strength or not, and these are examples where people tried to optimize the property of polyvinyl alcohol. Swelling pressure is another big consequence of a lot of things that occur in terms of confining the space where these hydrogels are to go, so osmotic pressure makes a big difference in terms of the way they perform. For lubricity, you have to go through freeze-thaw cycles. You do want to have compatible hydrogels, so where your stress is pressed upon the material, your coefficient of friction should be to the point where it can be lowered as much as possible. And here's examples of where they lowered the friction of these materials, depending on their structure. In terms of morphology, I talked about this before. I don't need to say it again, but here's an idea of what you can do in terms of getting the property of the pore size versus the mechanical properties of the gels. In terms of permeability and strength, you could tune these microstructures. You can go through elastic moduli that are very different depending on how these things are made. So you have a lot of flexibility in terms of what you could design into these systems. Here's where I was talking about the nucleus pulpus before. So here's where they'd want to enter the hydrogel to make a impression in the spine. Oops. Next. Get out of this. Okay. Drug release profiles, something else you can accomplish with these things. Here's an example of what cross-link density does to drug elution rates. So in terms of tissue models, a lot of device design, functionality testing, biocompatibility assessment, regulatory testing, and procedure training is a consequence of creating these things for use in life. There's issues with natural tissues due to cost, ethical concerns, duration of viability, and reproducibility. Synthetic materials tend to last longer and are usually more consistent and have usually less problems than natural materials. There's a lot of tissue models that are developed. This is just an example of a smattering of things that are done in terms of structure of these things. So in conclusion, there's a similarity of hydrogels to natural tissue, suitable for tissue models, tissue replacement, and potential for biocompatibility. You certainly have a range of tunable properties for these things. Now I'm going to turn my talk into another area that's very common today. It's this whole concept of soft tissue augmentation used in plastic surgery a lot. In recent trends, there's more non-surgical procedures going on in plastic surgery than ever before. You probably have heard of Botox injections, soft tissue fillers. People do chemical peels, microdermabrasion, laser hair removal. There are 6 million non-surgical cosmetic procedures going on these days. And 45% of the patients who get these things are repeat patients. And 32% have multiple procedures at the same time. There's a lot of media coverage relevant to these things. There's been improvements and increases in non-surgical treatment options that has sparked a greater interest in all age categories. There's new soft tissue filler options, many of which involve hyaluronic acid, and longer acting products that are actually polymeric in nature. Calcium hydroxyapatite, which is really the structure of the material that creates your bone. Poly-L-lactic acid that's been used as a building block for resorbable polymers. It turns out that poly-L-lactic acid lasts a very long time. It takes up to 2 years for that polymer to degrade. There's improved laser options and peels and dermabrasion and home remedies these days. So there's a changing paradigm in terms of soft tissue fillers. There's a plethora of new products. People do use collagen, has a longevity of 2 to 3 months, hyaluronic acid 6 to 9 months. There's been combinations of Botox plus collagen and hyaluronic acid to demonstrate longevity, and injectable calcium hydroxyapatite and polylactic acid lasting 2 years or more. The recent trends are there's non-surgical procedures growing at a fast pace for men and women. Botox is still the most popular, but there are more soft tissue fillers approved in the last 10 years than there have been in the last 50. There's increased options are changing towards the physician and patients toward non-surgical cosmetic enhancement. There's 2 types of Botox out on the market today. There's a type A and a type B. They're derived from different strains of the bacteria that create them. They're formulated to be delivered as a typical injectable, so there's really not any issue in terms of creating the right formula to inject these things. The collagen products that are out there are bioengineered and in many cases contain lidocaine to decrease pain. They're usually derived from human dermal fibroblast cells and they're grown on scaffolds to produce natural collagen. The duration of their effect is 2 to 3 months. The hyaluronic acid fillers are usually cross-linked. They're highly hydrophilic. They have a short half-life, but in order to retain a longevity, they must be cross-linked. There's several of them on the market today. One of the most popular named Restylane. There's Juvederm, Perlane, Purigen, Elevis, and Restylane Silk. These are the typical cross-link agents that are used. There's BDDE and DFS, and one is butane dialkyl diglycidyl ether, the other is divinyl sulfone. What they result in is different particle sizes and different concentrations of the hyaluronic acid. So there's another called Sculptra. That's injectable poly-L-lactic acid. It's actually crushed polylactide. It's made into small particulates. Its first use was for HIV patients who suffered from lipoatrophy and wanted to have their tissue rebuilt. So this was the material that was created for that. And in the US, it went through a humanitarian device exemption, and that's how it got approved for use. There's calcium hydroxyapatite. Like I said, this is the material that's commonly used to grow bone, but it's also used as a filler. These are spherical in nature, and they tend to be used for long-term repair of soft tissue. The common product that's out there today is called Radiesse. It's used in oral maxillofacial defects, vocal cord insufficiency, and it's also used as a tissue marker. There's combinations of these things used. There's these polymethacrylate microspheres, which are unfortunately permanent, which is not really the best solution for something like this, but it was developed several years ago and approved in the US. Their mode of action is to be delivered with a bovine collagen solution as well as a pain management compound, lidocaine, and once they're integrated, they remain in the area for a long time. There's commercially available products, many developed in many places, and the FDA has a general and plastic surgery devices panel that goes through these things constantly, and this is an example of where they were considering the use of Artifil, which was this polymethacrylate material as a filler. There's other ones that are developed on the market. People do use autologous fat. There's also isologen, which is a patient's own fibroblast cells, and there are cadaver-based products as well. So there's a lot of combination therapies today with fillers and Botox. Botox has really increased the confidence of treating lower and mid-face muscles. And today, by adding other things, they're able to enhance the longevity of the combination of treatments that are used. There's another group that developed the use of Botox and Restylane. And in the procedure, you will see that in a lot of cases, they'll inject these things to take care of nasolabial folds. They're injected into the upper, middle, and lower dermis. And the technique commonly uses volumes of 0.5 ml up to 2.5 milliliters of material. So before injection, you may have these defects, but after its injection, you see that you're getting a planar material again, and your skin readjusts to the shape of the filler that's in the bottom. So on the international front, there's about 60 products right now, and some are permanent, some are resorbable. The better ones tend to be the resorbable materials. There are unmet needs. They'd like to have more like an 18-month durability. For permanent, these things must be safe. There must be easy and convenient application of these things. For volume retention, the physicians usually say what you see is what you get. What they're looking for is a full product range offer, being non-palpable, non-migrating, non-immunogenic, and non-inflammatory. Here's another example where a defect is taken care of by a filler that's put into the dermis. and in other cases, different ways to deliver these things, either by a line, multiple injections, different lines, different matrices. And absorption profile is important in terms of longevity. So depending on where you inject and how you inject. This is an example of competitive landscape of materials, some of which have, well, this is missing the titles, but this was supposed to compare properties of these materials and what fillers fulfill those properties. In terms of a competitive landscape, you've got things that can solve issues in upper dermis, lower dermis, and middle dermis. And again, look at different properties of materials versus cost, and you can see that these things are not cheap to apply. An injection can cost you anywhere from $400 to $1,600 for these procedures. Regulatory assessment in the United States, like I said, the first one with polylactic acid went through a humanitarian device exemption, not something you really want to do in terms of getting a product approved. But in most cases, they go through PMA, and in some cases, you can get 510K if you have the right predicate around. So that's my talk, and I just wanted to give you an overview of where things are in terms of this field. And if you have any questions, go ahead and ask me. I think I almost took all my time.